So I'm going to introduce area in polar form. So first we're going to put a polar coordinate system. Do a little curve going on here. So this is a typical polar curve. In the XY sense, this is not a function. It fails the vertical line test, as you can see there. But in the polar sense, if this is f of theta, then it is a function. So how does this work? Well, we're going to find the area from some given theta value, theta equal to A, up to theta equal to B. Okay. And the area that we're finding is shaded in here. That's what we're looking for right there. All right. Now, how do we do this, right? How are we going to figure out the area of that shaded region? Well, what I'm going to do is think of it kind of like whenever we were in Cal 1, whenever we first talked about the definite integral and area under the curve. We took that really hard problem and we broke it up into little rectangles, right? And those rectangles, base times height, the height was f of x and the base was that delta x. And we summed the f of x delta x from A to B, okay? So we're going to take that same approach. We're going to find one little section here, okay? And so one little section ends up looking like a little sector. Now, how do we find the area of some sector? So d theta there. Well, let's take a circle, and then I'm going to take this angle to be theta here, and I want a radius r for that circle. So how do I get the area of this sector here? Well, let's think about it, okay? Area for an entire circle is equal to pi times r squared. But we don't want the entire circle, okay? We just want the angle theta of this circle. All right, so let's think about the angle theta. Well, how many degrees is in a whole circle, right? So in an entire circle, we go all the way around 360 degrees for a whole circle. 360 degrees is the same as 2 pi, okay? So for just this little angle theta that I care about, maybe that's like 30% of the circle, right? Well, how did you get that 30%, right? Well, if this, was like 3 and then all the way around was 10, then that would get you the 30%. So it's the part divided by the whole gets you that percentage, that area percentage that you're looking for. So the part is theta over the whole 2 pi. So that gets us a percent of what we want. So I multiply this by theta over 2 pi. And what happens? The pi's cancel each other, and this area reduces to what? It reduces to 1/2 r squared times theta. So the area of one little sector, one little wedge here, so if I take a tiny little wedge out, okay, sorry, this is not a right angle. So it's a little wedge there. I take a little delta d theta slice, okay? The radius r is that distance from the origin to the curve f of theta. So r is equal to f of theta. Okay, it's this little wedge. And so my formula becomes, it's 1/2 r squared theta. But now if I do it infinitesimally small, my theta is d theta, right? My r is the length from the origin, the pole, to the curve, f of theta squared. And then I have the 1/2 factor. And then I'm summing all those in infinite sum from A to B. Okay? So this area is equal to the integral from A to B of 1/2 f of theta squared d theta. All right, so that's how we find the area of this region. Kind of cool. So let's take a problem. I want to find the area of the cardioid. R equals 1 plus sine theta. R plus equals 1 plus sine theta. Okay. So cardioid, I'm thinking heart, and what does this look like on a graph? Well, at theta equal to 0, so if I think in the old sense of xy, right? The x input spits out the y value, right? So if I think of it in that sense, then theta tells me what r is going to be. So at theta equal to 0, so if I have an angle equal to 0, I'm on that terminal axis here, okay? And if I plug in 0, I get 1 plus sine of 0. Sine of 0 is 0, so that's just 1. So I'm right here at 1, okay, for theta equal to 0. Now, if I do like theta equal to pi over 6, then that gives me 1 plus the sine of pi over 6, which is equal to 1 plus a half, so that's 1.5. So at pi over 6, it comes out to 1.5. Excuse me. And then maybe if I do like pi over 3, that's 1 plus sine pi over 3, which is 1 plus square root of 3 over 2. Square root of 3 over 2. Let's see what that gets me. Square root 3 divided by 2 plus 1. So that gives me 1.8. So 1.8 is even further. So that would be an angle of pi over 3. Sorry, pi over 3 right there. Okay. So 1.87. And then pi over 2, what would that get me? Well, that's all the way up. That's on this vertical here. And so that'd be 1 plus sine pi over 2. And that'd be 1 plus 1, which is 2. And so whenever I get all the way up to here, I'm at 2. Okay? And then as I work my way back down, 2 pi over 3 that's going to get me back around here. And then, so once again, if you run through this, sine 2 pi over 3, you get 1.87 again. And then 5 pi over 6 gets you back over to here. 1 plus sine 5 pi over 6 gets you 1.5 again. And then when I plug a pi in, 1 plus sine of pi, that's 1 plus 0, which is 1. And then 1 again. And then if I keep going, now all of a sudden my sines are going to be negative. So if my sines are negative, so like 7 pi over 6, so that's like 1 plus negative a half, that gives me 0.5. So what's happening now? Instead of my curve going out further away from the origin, it's actually going to get pulled back into the origin. And then as my angle gets closer and closer to 3 pi over 2, well, what do we know about the sine of 3 pi over 2? Well, that's equal to negative 1, so that would be 1 plus that would give me 1 plus a negative 1 gets me 0. So that 3 pi over 2 angle is going to get pulled right back into the origin, okay? And then once I get past that, then it starts coming back out again, and we make the circle back through. So that's a way to help you graph this by hand if you had to graph that by hand. You just plug in theta values, and as you plug in theta values, you evaluate the rule that gives you the output R value, how far away you are from the origin. Like for example, at pi over 2, angle of pi over 2, we're 2 units away. Well, what does an angle of pi over 2 look like? Well, I go up to pi over 2 here, and I go up 1, 2 units, and I put a dot, all right? Or if I was, say I was pi over 6, I go out to 1.5. So I go up pi over 6, an angle of pi over 6 here, and I go out a distance r equal to 1.5, and I put a dot there, okay? So that's what we're doing there. And so this curve here, r equals 1 plus sine theta, revolves about theta from 0 to 2 pi before I make that circle again. And if I keep going past 2 pi, I'm just going to keep making that same path over and over, as many 2 pi's as you go through. Okay? So let's find the area. Let's find the area of this cardioid here. To do that, what we're going to do is write up the formula. What does the formula say? It says integral a to b 1/2 f of theta squared d theta. So who are the players? Well, I start at angle 0, and then I rotate this thing all the way around pi over 2 to pi to 3 pi over 2, and then back to 2 pi to get the full circle, okay, the full cardioid. So I need to integrate from 0 to 2 pi to get everything, okay? That's why it's important to draw the picture so you know how far you're integrating from. Let me move this out of the way. We don't need this. All right, and now I have 1/2, and then f of theta. What is f of theta? That's my rule here. That's my r. So that's 1 plus sine theta squared d theta. Now, if you wanted to, you could do this by hand. But why do it by hand when you have a calculator? So let's use our calculator and get our answer here. So I'm going to do math, integral 0 to 2 pi. And then I'm going to do 1/2 times parentheses 1 plus sine. And since I have a differential x already, I'm going to use x here. The variable doesn't matter. Close the parentheses, square everything, and integrate. And lo and behold, I get 4.712. 4.712. Now the exact answer here, just for funsies, the exact answer is 3 pi over 2. Okay? If you were going to do this in your calculator and you didn't have the software like you see on the left here, it would be math function integrate, so fn integrate, and then you put the 1 divided by 2 parentheses 1 plus sine x, close parentheses, square it, and then you would do the comma. So let me make this smaller real quick. And you have x as your variable, 0 to 2 pi, and then close it up, hit enter, and you'll get the same answer there. Okay? So hopefully that helps you understand what's going on there with a simple cardioid and how to find the area of that enclosed region. In the next video, I'll talk about what we do whenever we've got two different curves and we're trying to find the area between